Welcome to this second lecture about heat pumps. In this lecture, we address solely the heating mode. Let's take again the flow diagram of the heat pump. We have already made an energy balance on the heat pump. Electricity in plus heat input from evaporator should be equal to the heat delivered at the condenser plus some heat lost in the pipes and the casing. As we are in heating mode, we are interested by the heat produced at the condenser side, the heat coming out of the condenser, and that we call the heat sink. The heat input at the evaporator is called the heat source. According to what we have learned, the efficiency should be defined as Q condenser out divided by compressor electricity in plus heat in at the evaporator. In a heat pump, however, this heat input at the evaporator side is meant to be free environmental heat from the air, the ground, or a river. It is fully renewable, so we don't account for it, and instead of using the thermodynamic efficiency, we will use the coefficient of performance, the so-called COP, which is defined as Q condenser out divided by the electricity needed by the compressor. Except if the heat loss are extremely high, this COP will always be above 1. But there is something more. Just like it is impossible when burning a fuel to get more heat out of it than its higher heating value, there is something like a maximum achievable COP. This maximum COP is called the Carnot COP and is defined as being the ratio between the high temperature side TH and the temperature difference between the warm and cold side, TH minus TC. TH should be in Kelvin, of course. Let's take the example of a heat pump with a low temperature TC of 7 degrees as heat source and a high temperature TH of 70 degrees Celsius. The Carnot COP is then 273 plus 70 equals 343 divided by 70 minus 7, which is 5.4. Meaning that the amount of electricity needed is 5.4 times lower than the heat output, much better than with a resistance heater with its efficiency of 1. And this is possible because of the use of free low temperature energy as heat source at the evaporator side. This Carnot COP, is this the maximum COP we can achieve if we want to use the heat for radiator heating at 70 degrees using outdoor air at 7 degrees? Think about it. Unfortunately not, because nothing is perfect. Let's look at the complete system. The high temperature TH, 70 degrees, is the hot water temperature of the radiators, while TC is the temperature of the outdoor air. Perfect heat exchangers do not exist, and there must be a temperature difference between the outdoor air and the refrigerant in the evaporator, and also a temperature difference between the central heating water and the refrigerant in the condenser. In high quality or large heat exchangers, a temperature difference delta T of 2 degrees will be enough, leading to 72 at the condenser and 5 degrees at the evaporator, and the Carnot COP will then be 5.1. With lower quality or small heat exchangers, temperature differences of more than 7 degrees have to be used, and this would lead to a Carnot COP of 4.5. By the way, at cold temperatures, a defrost mode is needed, otherwise the humidity contained by the outdoor air would condensate and freeze on the evaporator, which would decrease its performances a lot. Generally, producers give the COP of their heat pump as being the Carnot COP times the Carnot efficiency. This Carnot efficiency accounts for non-ideal heat exchange in the evaporator and the condenser, and for all losses in the compressor and in pipes, valves and casing, and also pump and fan energy at the source and sink sides. The Carnot efficiency ETC is generally quite low. Most simple cheap systems like domestic room air conditioners in heating mode have a Carnot efficiency below 0.3, Only the better heat pumps with high efficiency heat exchangers will achieve a Carnot efficiency around 0.6. We have seen that the COP is strongly dependent on the temperature level. Many heat pumps use outdoor air as heat source. The temperature at the evaporator will vary a lot during the winter, and this will cause huge variations of the COP. In general, the COP varies also with the load, and we know from the course energy demand in buildings that the heating equipment will almost never be needed at full load because the energy demand varies a lot all over the year. This is why producers of heat pump must specify the COP for different outdoor and load conditions and provide a formula to calculate the seasonal COP depending on the frequency of occurrence of partial load for a certain climate. This is the so-called SCOP, which is representative of the average efficiency of the heat pump over a complete heating season. So, if you know the annual heating demand in a building and you know the SCOP, you can then estimate the needed electrical power, Q demand divided by SCOP, which should be the same as the annual condenser heat output divided by the SCOP. In the example we have treated, we took outdoor air as heat source. There are, however, many other heat sources that can be used. Look at this graphic. Water, for instance, has much more mass than air and is generally warmer in winter, so we could use a pond, lake or the sea as heat source. The shallow ground, between 1 and 10 meter depth, has an even more stable temperature, almost constant all over the year. Let's look at how the choice for a specific heat source and its temperature Tc influences the COP and therefore also the SCOP in approximately the same share. Imagine again that we want to produce hot water at 70 degrees Celsius for the radiators of the central heating and the Carnot efficiency is 0.4. We use first a heat pump with air as heat source. Imagine the average outdoor temperature is 3 degrees during the heating season. The COP will be 2.1. If the building is close to a lake or the sea, we could also use them as heat source. As already mentioned, this water has a higher temperature than the air during winter. Let's take an average of 7 degrees. This leads us to a COP of 2.2. We gained 4% in efficiency. If we place now a ground heat exchanger, as the ground has a temperature of 9 degrees, this leads to a COP of 2.3, again of 10%. And maybe, if there is a mechanical ventilation system in the building, we could use the warm exhaust air as heat source. We would then have a heat source at 20 degrees, which would allow for a Carnot COP of 2.7, a gain of 29%. It is therefore extremely important to choose a high temperature heat source. You see here some examples of heat sources. In the first and second ones, the heat source is the ground and a pipe filled with, for instance, water and glycol is circulated in a closed loop through the ground and connected to the evaporator. The first one is a vertical heat exchanger, very useful when there is not much space, like in a city. The second one is an horizontal one, easier to place but asking for a large surface. These types of ground heat exchangers are suitable for small buildings. For large ones, other solutions like aquifer thermal storage have to be applied or groundwater heat pumps. In a groundwater heat pump, the vertical heat exchanger goes deeper in the ground until it meets an aquifer. Below, you see that the heat exchanger could also be placed in a pond, and on the right you see the evaporator of a heat pump using outdoor air as heat source, the most common ones. We have looked extensively at the heat source temperatures, but what about the heat sink and the temperature TH at which the heat is delivered? In the formula for the COP, we see that it also has an impact. Let's take the ground source heat pump as an example, with a source temperature at 9 degrees and again a Carnot efficiency of 0.4. We have already seen that with central heating at 70 degrees, the COP would be 2.3. If we now use central heating with a lower temperature of 50 degrees, the COP increases to 2.7. If we have installed floor heating, the heating temperature TH will be around 40 degrees instead of 50, bringing this time the COP to 4.7, an increase of 104%. And finally, if we would use direct room air heating at 20 degrees, the COP would increase to 10.7. That's a lot. Cold tap water has a relatively low temperature, in moderate climates around 9 degrees, much colder in cold climates, and hot water should have a temperature around 50 degrees Celsius, and once a week 60 degrees to eliminate the Legionella bacteria. This may be a problem for heat pumps, as we just have seen that they prefer low temperature differences. If the heat pump has to bridge a temperature difference from 9 to 60, its COP will not be much higher than 2. Additionally, hot tap water asks for a very high instant power because no one wants to wait for minutes on warm water. The more power, the higher the investment costs. Both facts generally lead to the choice of hybrid systems, in which the heat pump provides the basis hot tap water heating, let's say up to 40 degrees, and an electrical resistance heater bridges the last 10 to 20 degrees. The electrical resistance may also be replaced by a gas boiler or solar heat. Heat pumps for hot tap water are generally coupled to a cylinder in such a way that the heat pump can take its time to fill the cylinder with hot tap water while having a limited power. This will save costs. However, such a cylinder will cause additional heat losses through its casing, also if it is well insulated. Up to now we have handled the compression heat pump, but what about the absorption heat pump with its thermal compressor? Well, from the energy balance we can deduct here too the COP, which is useful heat out divided by electricity input at the pump. If we are not accounting for the input from the waste heat, sometimes the heat delivered at the absorber has a temperature high enough to be useful and is therefore accounted for in the heat output. When this is not the case, this low temperature heat is just wasted. When the desorber is not using waste heat but heat generated for this purpose, we must account for it in the denominator. The COP is the Carnot COP multiplied by the efficiency of the thermal compressor, which can be shown to be the temperature of the heat input at the desorber minus the temperature in the evaporator, Tc, divided by Tc. In general, the efficiency of absorption heat pumps is much lower than the one of compression heat pumps, except if waste heat can be used to drive the thermal compressor. Let's look now at the primary energy and CO2 emissions. Imagine we have an electrical heat pump with a seasonal COP of 4. The space heating demand is 3000 kWh, therefore we need 3000 divided by 4 equals 750 kWh electricity to power the heat pump. Electricity is final energy, meaning that it is delivered to the building. This electricity must be made in a power plant. Let's consider it is produced in a gas power plant of efficiency 0.4. So the annual primary energy is now 1875 kWh. So the true efficiency of electrical heating with a heat pump is not 4, but 0.4 times 4, which is 1.6. And how much gas is that? Well, the higher heating value of North Sea gas is 9.8 kWh. Dividing the primary energy by this heating value gives us the quantity of gas, which is 191 cubic meter, 4 times less than when using a simple electrical resistance heater. Evidently, the CO2 equivalent emissions decrease accordingly. If electricity was produced by renewables instead of gas, we could then consider the primary energy to be zero. The CO2 emissions will be zero as well. In this lecture, you have discovered how the COP of heat pumps is determined by the temperature levels of the heat source and heat sink. To obtain a high efficiency, it is very important to limit the temperature differences between the sink and the source. This is why high stable heat source temperature are preferred. At constant sink temperature, a ground source heat pump will have a higher COP than a water one than an air one. Low temperature heat sinks are essential as well for high efficiency, and low temperature heating systems are preferred like air ones or floor heating. When making estimations of primary energy use over a year, it is recommended to work with the seasonal COP. And finally, heat pump boilers for hot tap water will have a lower efficiency and will be aided by an additional electrical or gas heater. Thank you for your attention.